Okay, let's get started. Welcome to the week 6 live session of the GPU Architectures and Programming NPTEL course. So, this will be a 2-hour session where we focus mainly on problem solving but also go through some of the doubts and questions that are asked in the previous weeks. And post the session, you will get access to the slides and the recording. And feel free to post any questions and doubts on the chat box. And we will have a short 5-minute break around the 8 o'clock mark. Okay, with that, let's get started. So, week 6, the course contents were mainly around memory access coalescing. So, we looked broadly into the memory spaces, the different types of memory that are available in a GPU, starting from the registers going all the way to global memory or DRAM. And then we looked at the types of memory access. We spoke about how do you coalesce memory accesses to get better performance. Then we looked a little bit about profiling, where we looked at profiling with NBProf, and we also spoke about profiling using CUDA events, right? And then we took two specific examples of matrix multiplication and matrix transpose, and in both cases we looked at several optimizations like tiling and what is the performance implication of doing a naive row versus naive column and lots of things like that, right? So today's content will be broadly around these things. So with that, let's start with a recap of week 6. Again, as always, this will be on selected topics, not everything that was covered. But if you haven't understood something particularly well, feel free to ask for that. Okay, so let's talk about memory spaces. So here's a quick recap. So given that you have threads, the first type of memory that you have, the closest one, is the registers. And then you have shared memory. So shared memory is shared across all threads in a given block, whereas registers are for a particular thread, right? And then further, after registers and shared memory, you have global memory, which is common across all the threads and all the blocks. Okay, so coming back. So global memory is common to everything, and apart from that you also have things like constant memory, where you can store some things that are common to a lot of computation. Hope you can see my screen and hear me clearly. If there are any issues, please post on chat. Okay, moving on. Great, good to know that. Moving on. So types of memory accesses. So global memory is the slowest, shared memory is much faster, and registers is the fastest. I think in the very first class we kind of compared this GPU memory hierarchy with the CPU memory hierarchy, right? Where we pointed out that there are registers and there are different levels of cache, and then finally there is main memory, and then thereafter there are all these types of storage media like disk and much older forms of disks like tape drives and all of that, right? And typically the speed also is like this. Registers are the fastest, and then you have some kind of cache memory, and then finally main memory, right? So here also it's the same. Registers are the fastest, shared memory is a little slower than registers, and then global memory is the slowest. So this is the latency wise looking at the different types of memory. Then so when you have a warp requesting some memory, what the GPU does is it coalesces these global memory loads and stores. Let me just get a pen. Yeah, so it coalesces these that are requested by a warp, right? What is the advantage of doing this? Instead of doing multiple loads and stores, you can kind of do it at the same time, and that gives you better performance. And since you have this notion of a warp of threads where all of them typically work on the same instruction, this is also going to give you benefits by doing this coalescing, right? Why does it give you benefits? Because typically it requests for 32 aligned 4-byte words in one global memory transaction. So when you do this coalescing, you're going to reduce the number of transactions that you do for a bot, and because of that your execution time comes down and becomes more optimized, and you get those benefits in execution time. So but here again, the programmer or the user should come up with memory access expressions that kind of help you do this. Okay, moving on. So next, talking about profiling. So you can do two types of profiling, right? One is where it's very fine grained, where you as a programmer say that okay, I want to know the time taken for this particular event, so I'm going to add this kind of log or instrumentation. Let's say there is one particular function, right, that you want to profile. So let's say you add a log before it, after it, that will kind of give you the time taken for this function, right? This is one kind of fine-grained profiling. So this is what we are talking about here. So for this, we use the CUDA event API. So there is a CUDA event underscore T that you can use to declare one of these CUDA events. And you can create and destroy them using these APIs. And you can record timestamps using CUDA event record. And then the time elapsed between two recorded events would be given by this. So basically you have all these APIs that are very convenient for you to do such things, figure out how much time elapsed between something, measure all kinds of things, right? But the second kind of profiling, where things like NVProf, right? So I think NVProf is a bit outdated now. Currently, I think NVIDIA has these tools called Nsight, and Nsight systems and Nsight compute is what they recommend for profiling. But NVProf was the equivalent of that. So this is kind of automatic or implicit profiling, where you don't add such logs anywhere, right? You just run a program calling NVProf and say, let's say, collect all GPU statistics or collect all memory statistics, right? So what NVProf will do is it will collect these statistics pertaining to multiple events or metrics at the same time. You don't have to go and explicitly add these logs everywhere, because that might be very painful, and sometimes you might also want to measure very low level things, right? For instance, in a particular kernel, how does the launch look like, or what is the launch time? Things that you cannot measure by simply putting logs around this, right? So in those cases, these profiling utilities that are shipped by hardware vendors are more useful. So here again, the difference is you don't have to use an API like CUDA events. Any doubts so far? Anything that's not clear? Okay, great. Next, moving on to shared memory. And again, I think we spoke about this in earlier weeks also. Each SM typically has 64 KB of on-chip memory, and you can partition this between the L1 cache and the shared memory. Typically what we do, we keep 48 KB for the shared memory and 16 KB for the L1 cache, or vice versa. You can have 16 KB shared memory and 48 KB L1 cache. And by default, the setting is that it's 48 KB shared memory and 16 KB L1 cache. Again, all of these can be configured using runtime APIs from the host, using this CUDA device set cache config, where you do this on a so this CUDA device set cache config is for all kernels, right? If you want to do it on a per kernel basis, you can do the function set cache config. Depending on how you want to change these settings, you can call the API accordingly. If not, the default setting would be used. Okay, with this, I think we are done with the recap. Any other topics from week 6 that were not clear? Any doubts? I'll just wait 30 seconds. You can think about it and see if you have any doubts on the all of week 6 contents. If so, I'll pick it up in the next class, or if I have content in the form of slides, I'll explain it today itself. Assignment questions, I see. Okay. I think we have a good number of assignment questions coming up next. So let's do one thing. Let's discuss those assignment questions. And if you still have a doubt after that, then you can point me to the specific questions that you're not clear with, and I can explain them in the next week. I think by then the deadline for the assignment submission should also be over. I think it was already over, and I think the solutions are also released. So we can definitely discuss them. Let's go through the questions that we have today, and then after that, if you still have doubts, we can take up those particular questions. Okay, if not, let's go to the next set of questions. Okay, I think I found only one question on the discussion forum this week. Looks like there are a couple more yesterday and today which I have not yet looked at, so I'll cover that in the next week. But this was basically about the matrix transpose, right? So in class, I think there was this picture drawn where the instructor spoke about the block 0 0 being flipped to block 1 comma 1, right? So this person was confused about that and worked out the transpose manually and showed that the elements of block 0 0 should be still placed in the block 0 0 itself in the transpose matrix and not 1 1 as explained in class. So the clarification to this was that block IDs are flipped. So 0 0 will still be 0 0, not 1 1. Basically, your x comma y will change to y comma x. So what was shown in class as 0 0 being flipped to 1 1 was a mistake. So ignore that. Just understand that it is kind of flipped. It won't go from 0 0 to 1 1, right? I think that was what was confusing. So that is clarified as being wrong. So this was the only thing I found about the discussion forum. So let's move forward then. So I think most of these questions involve working out something. So I'll read the question and then I'll give 2 to 3 minutes for you to solve it, and then we can look at the solution together. If you have an answer, you can put it on chat. It doesn't matter if it's right or wrong. It's fine. Okay, so the first question: 16 consecutive floating point data values can be brought in a single global memory transaction. Consider an array A comprising of floating point values and a GPU architecture with warp size 16. For the array access expression A of TID, where TID equal to block ID x dot x into block dimension dot x plus thread ID x dot x, what is the total number of global memory transactions if the total number of threads launched is 256? Take a couple of minutes to work it out. Any answers so far? Okay, 8. Okay, then let's take a look at the answer. So it is 16. Let's look at why it's 16, right? So threads in each warp access consecutive elements. So because we are accessing A of TID, where TID is given by this, right? And we are also told that warp size is 16. So every warp performs a global memory transaction because we've studied the whole memory coalescing, right? So if you have different threads accessing, let's for simplicity say that warp size is 4, right? And if all of these 4 elements are being accessed, what we would do is to coalesce these accesses, meaning we would do only one global uh, load for all 4 threads in the warp. Similarly, here we have warp size of 16 and we have a total number of threads given to be 256. So the total number of warps is 256 by 16, which is 16. So the total number of memory transactions also would be 16. Why would it be equal to number of warps? Because you're doing one transaction per warp. And why is it one transaction per warp? Because you're accessing consecutive elements. If you are accessing, say, elements that are offset by something, for instance, if you're accessing alternate elements, as we saw in class, and I think as there are other questions also in this session, the number of accesses can be a lot more than number of warps. But here, since it's consecutive elements, we can coalesce all of them into one access. So hope this is clear. I'll just wait here for a few seconds before going to the next question. Great. Let's move on then. Considering the same GPU architectural configuration and the number of threads launched in question 1, which is basically 256. Now, what would be the total number of global memory transactions for A of TID plus 1? So, this is the new question. Again, take a couple of minutes to think about this. Yes, please tell me. Do we need to submit subjective assignments? Let me see. Are those programming assignments similar to what you had in week 3 or something like that? Okay, then I think you need to submit that. There is a submission link and all of that, right? In week 4. Okay. Let me just take a look. I have the. Okay, week 4. Right, I think the deadline says that it was Feb 22nd, right? So you missed submitting to this deadline, is it? Okay, then you will have to ask the TAs, but I think typically they give 2 weeks time, right? So if you miss that submission deadline, I'm not sure if they will accept a late submission. But you do have to submit the subjective ones also. Oh, 1 week. Okay. I see. Yeah, you can also ask saying if you think you need more time, you could also request saying next time that you would like to have 2 weeks for a subjective assignment. Maybe they will take that into account. But I think so far after week 4, there hasn't been a subjective assignment, right? Only the week 4 was the only one. Okay, okay. Right. So you can ask for that. That should be doable. They can release it a little in advance. This also you can ask, but I'm not sure they would consider it because I think the solution also would be already released, right? So not sure if they will take a late submission. Oh, you can ask on the discussion forum itself. So if you go to the course, I think you'll see this button saying ask a question, which takes you to this Google Groups where people ask questions, right? Like the question I discussed in the just now was also from the discussion forum. I'll also see if I can share the link of the discussion forum here that you can use quickly. So the official TS would be looking at this forum. So you can use this to give your feedback and suggestions and ask for clarifications also. No problem. Okay, coming back to the second question. Any answers so far? We'll wait 30 more seconds and then look at the answer. Okay. So here the answer is 32. And again notice that it is the same number of threads, the same GPU, right? Just because you are doing A of TID plus 1 rather than A of TID with the same warp size, the same number of threads, the same GPU, now your memory access is double from 16 to 32. So let's again take a quick recap of why that is, right? So here you have an offset of 1, this TID plus 1. So every warp would require 2 memory transactions. So here is an example, right? Warp 0 would require 1 memory transaction to fetch the elements 1 to 15 and then 1 more to fetch 16. So every warp would this way require two memory accesses. So one for this full thing that is aligned, and then one more for the 16, which is kind of in the next row in the global memory, right? So, and you have so for every warp you need to do two global memory transactions, and you have a total of 16 warps. So it becomes 16 into 2, 32, as opposed to the last time where you could just fetch everything in one access. Any doubts here? Okay, great. Okay, considering the same GPU architecture configuration and same number of threads, what would be the total number of global memory transactions for A of TID star 2? So very similar question, just that your axis expression changes. 32. Okay. Let's look at the answer. Yes, 32 is correct. So here, this is called stride. So these are kind of standard terminologies, right? When you do a plus, you typically talk about it as an offset. And when you do a 2, it is called a stride. So it's basically like this, right? What is your stride? And if you do a plus 1, it's plus whatever, plus some n. That is spoken of as an offset. So here you have a stride of 2. So again, each warp would require two memory accesses. So you'd access 0, 2, 4, 8, 10, 12, 14. All of this in one transaction, and then from 16 to 30 in the other transaction. So again, for a warp you would take two memory transactions, and for 16 warps you would take 2 into 16, which is 32. So again, interestingly here, you notice that whether it's TID plus 1 or TID star 2, it is taking the same number of memory accesses. So these are all things to keep in mind when you write your own GPU program, right? A simple, the way you access your array might make a lot of difference, how you access it. And that has an implication on performance also. So it's something to keep in mind. Okay, so very similar question again. Considering the same GPU architectural configuration and number of threads, what would be the total number of global memory transactions for A of TID plus 16? So this is an offset of 16. Okay, we have an answer saying 64. Okay, let's take a look. Okay, surprisingly it is 16. So let's see why that is, right? So consider the threads in warp 0. So you have 16 of them numbered from 0 to 15, but they would be fetching TID plus 16. So they would basically be fetching 16 to 31. This 16 is your offset. But what happens now is this offset ensures that your elements are aligned. So let's go back to this figure. I think this will help us understand, right? So earlier we were talking about fetching from A0 to A15, right? Now instead we are fetching from A16 to A31. But if you see that, that is aligned. It starts from here. So you're not fetching something from 17 to 32. Instead, because the offset is kind of aligned to this row size, you're actually able to do the whole thing in one axis, even though the offset is non-zero. So therefore, this becomes equivalent to A of TID, basically an offset of 0. You just need one global memory transaction per warp, and you have 16 warps, so the total number of transactions would be 16. So any offset of the form, so TID plus, so if 16 is your base size, right? Anything that is a multiple of 16, for for instance 32 also, right? If you had to do this plus 32, you would start accessing a few rows later. Now you're accessing from the third row. Instead you would be accessing from the fifth row, but the accesses would still be aligned. So it doesn't matter whether you're accessing the third row or the fifth row. All it matters is how many accesses do you need to do. And because it's aligned to the 16, you will just need to do one axis. So anything of the form this n cross 16, where your offset is a multiple of 16, would result only in one axis per warp. So your total number of axes don't go up. It remains at 16. Any doubts here? Oh, the one would be per warp. Right, this one would be per warp, and you here we're asking about the total number of transactions. So you have 16 warps, and that becomes 16 into 1, 16. We typically coalesce accesses only per warp. We don't do it across warps. So whatever we talk about, this whole thing is for a warp, and then you multiply it by number of warps. Okay, let's move on to the next question. Consider the following code snippet on a GPU architecture where the number of shared memory banks is 32 and the bank width is 4 bytes. So set row read column, and you have a tile of size SZ where SZ is 32, and GID is defined this way: threadidx.x cross block dimension dot y plus threadidx.y. Tile of threadidx.x threadidx.y equal to GID. You have a sync threads after that, and then you have two blanks for TIDX and TIDY, and finally you're populating your output out of GID as tile of TIDX TIDY. Now the question is, this kernel is launched with parameters 32 32 32 32. Consider the last shared load operation, which is this one, tile of TIDX TIDY. You're loading that. So this depends on the values of TIDX and TIDY. Now if TIDX is threadidx.y and TIDY is threadidx.x, the shared load transactions are bank conflict free. true or false. I'll pause here for 30 seconds and go back to the previous part of the question. Okay, I've scrolled back. You can look at this and tell me when you have an answer. I'll wait maybe 3 minutes since it's a bit long. Excuse me. Okay, the answer is false. Okay, let's take a look at that. So it is true, the transactions are bank conflict free. So let's see why that is. So now the size of the shared tile is 32 cross 32 and the number of banks is also 32. So every column of your tile gets mapped to a single bank, right? So you have 32 of these. Now your launch parameters are given and it's 32 comma 32. So your warps look like this. Warp 0 has from 0 0 to 0 comma 31 and warp 1 has 1 0 to 1 31 and so on. Now the first element of each pair. So here going back to this one, tile of TIDX, TIDY, that's your axis, right? And TIDX is threadIDX dot y and TIDY is threadIDX dot x. So the first element is threadIDX dot y and the second one is the threadIDX dot x. So for any warp, if you look at this, the values of the threadIDX dot x change for a fixed value of threadIDX dot y. So if you see here, going by our usual convention, right? We have y here and we have x here. So y is 0 and the x keeps on changing from 0 to 31. So if you do an axis of the form threadIDX dot y, which is going to be fixed to 0 and your x would change, right? Now if you do this axis, then it would be bank conflict free because threads in any warp access elements from different columns. So you would be doing something like this 0 comma 1 0 0 2 0 3 and so on, right? So all of them would be in the same row but they would map to different bank columns and there would be no conflict, right? Whereas if you did something like 1 0 1 1 1 2, then all of them would map to the same column and there would be conflicts when the warp tries to access these elements. But in this case, because you do y and x, there is no conflict because of the way the tiles are mapped to the columns. Is this clear? Great. Let's move to the next one. So for the same code snippet, now what we do is tidx is threadidx.x and tidy is threadidx dot y. Now are the shared load transactions still conflict free? True or false? Take a minute and think about it. Okay. Assignment model questions are not taught in the lecture classes. Right, right. I think that's why they are introducing these live sessions, because in the lectures you don't have uh, time to kind of do these questions in the 2 or 3 hour content that is released to you. You basically, the professor kind of covers the concepts, but these live sessions help you apply those concepts to the problems. But I understand what you say, because the assignment deadlines are before we kind of discuss these questions. So, and the reason that is these questions are very similar to what is given in your assignment, and sometimes they are the same also. And that's why they kind of make us solve them after the deadline. So it won't help you solve those questions directly, but hopefully you will, as you attend more of these live sessions, you will understand how to take those concepts and then apply them to solving questions. You can also look at previous years live sessions. I don't know if there are videos on YouTube, but you can check and see if people have done a similar thing. I'm not sure if, I think these live sessions have been going on for a year. I have not done these live sessions last year for this course, but you may be able to find other people who have solved similar questions, and that might help you solve them. That's the only suggestion I have as of now. But in terms of how we cover it here, I don't have much flexibility, because the live sessions kind of started 2 weeks after the course, so there is always that lag of 2 weeks. So by the time I come to a particular week's problems, I think your assignment deadlines are already over. So if anything, this will help you for your final exam, but not the individual assignments themselves. Okay, coming back to this question. Any answers to this? Okay, false. Yes, it is false. I think, as we discussed in the previous problem. So here we've kind of reversed it. We are using x as the first tidx and y as tidy. So you'll end up accessing everything of the same column, right? Every warp maps to one single column and of the bank, and that results in conflicts. So the statement that the transactions are conflict free is false. They definitely have conflicts. So let's move on to one more question and then maybe we'll take a break. Okay, same code snippet as 5. Now your tidx is threadidx.x, tidy is threadidx.x. Now do the shared load transactions have bank conflicts? Think about this. This is slightly different. Okay, we have an answer saying true. Okay, let's take a look at the answer. It is false. So why is it false? So if you try to access tile of threadidx.x, threadidx.x, it's basically like accessing the principal diagonal, right? Remember that in this here the x varies. So if you look at a particular warp, the y is fixed while the x kind of varies. So what happens then is you're kind of accessing things along the diagonal, something like 1 1 2 2 3 3, and all of those are obviously in different columns, so you don't end up having any bank conflicts. So again here, the statement that it has bank conflicts is false. There are no conflicts. Is this clear? Okay, great. Let's do one more question maybe. So for tidx equal to threadidx dot x, tidy is sz minus 1 minus threadidx dot x. This variable was I think 32, so you can take that into account. And again the question is whether the shared load transactions are conflict free. So take a couple of minutes to think about this. If this seems too difficult to reason out very uh, in an abstract fashion, try putting values into tidx and tidy and see how it maps to the banks. Okay, we'll wait another 30 seconds and then discuss the answer. So the answer is true again here. So if you look at this, okay, so this should be x comma y, not y comma y. I will just correct this here for the time being, and then in the final slides I'll also make the correction. So this is like accessing your non-principal diagonal elements. In the previous question we were doing, I think, x comma x, right, which comes out to something like this. Now here again your x value changes, and your y is 32 minus 1 minus x. So it's 31 minus x, right? So if your x is 1, it will be 31 minus 1, which is 30. And if it's 2, it will be 29, and so on. So it's basically accessing non-principal diagonal. But again, all accesses from a warp will be along different columns. So again, you will not have any bank conflicts. Is this clear? Okay, so let me repeat that. So here in the previous question, your TID x and TID y were the same. Both were thread idx.x. So we said that this is basically like accessing the principal diagonal elements of your in your when you visualize these banks, right? So they come to different columns and there are no bank conflicts. And here what happens, your x remains the same. TID x is thread idx dot x. TID y is sz minus 1. So this sz is given as 32, right? So this 32 minus 1 is 31. So 31 minus thread id x dot x is your y value. So if your thread idx dot x is 1, 31 minus 1, which is basically 30, is your y, TID y. And similarly, you will have 2 comma 29, 3 comma 28, and so on, right? And this is essentially like accessing your non-principal diagonal, all elements except this, right? But again, notice that the accesses are not going to the same column. Your accesses will never end up like this with conflicts. They will end up somewhere here. So for instance, this is 1 comma 30, right? And then you have 2 comma 29, and then you have something like 3 comma 28, and so on, right? All of these are on different columns, so you don't have any bank conflicts, and the statement that the loads are conflict free is true. Now is this clear? Okay, so I think we'll take a break before we go to the next question. Let me just take a look at how many we have left. Okay, we have around 4 left, I think. Okay, so this is a good place to take a break. I think it's almost 8:04 now, so we'll come back at 8:09. So I'll stay on the call, but take a 5-minute break and then we can resume. Okay, let's continue. Consider the optimized shared memory implementation for matrix multiplication of matrices A and B. For a matrix of size 1024 into 1024, a tile width of 64, and a GPU architecture with warp size 32, what would be the total number of memory accesses that would be required for only loading shared memory tiles of A and B? Take 2-3 minutes for this. Again, I think it involves a good amount of working out. Any answers so far? We'll wait a few more seconds and then look at the answer. Okay, let's go ahead. So the answer is 4096, right? Let's maybe look at the so we are told that the warp size is 32, matrix size is 1024 into 1024, right? Before we come to this formula, let's take this pictorial representation, right? So you have two matrices. Let's consider these two as your A and B, right? So now the matrix sizes are n cross n, both of them are n cross n, and your tile size is W cross W, right? Now, what you're asked for is the number of memory accesses for only loading the tiles of A and B. Okay, so now what do you need to calculate this? How would you break this up, right? It is the product of the memory accesses to load one tile into the number of tiles for A and B. So let's talk about memory accesses to load one tile, right? So your tile width is W, your tile size, width and height are W cross W, right? Now what you can do is in one dimension, you can coalesce the axes, the row basically. So that will become W by 32, because whatever you can sort of coalesce that many axes in the row dimension. So that dimension becomes W by 32. Whereas the columns, you have to do that many loads, right? So that would remain as W. So to load a tile, it would take W by 32 into W. Basically this much for the rows and this much for the columns, right? And this is for one tile. Now, if you look at the size of the matrix, it is n cross n, and the size of the tile is W cross W. So n by W would give you the number of tiles for one matrix A. But you also need to load for B, so it becomes 2n by W. So the total number of tiles is 2n by W. So therefore, your total number of memory accesses becomes the product of these two. Memory accesses for one tile into the number of tiles, W by 32 into W into 2n by W. Now if you substitute these values, basically your W is 64, 64 by 32, which is 2, 2 into 64 into 2 into 1024 by 64. So you can straight away cancel these two. So you have a 2 left out from here and a 2 left out from here and 1024. So 4 into 1024 becomes 4096. So that is your total number of memory accesses for loading shared memory tiles of A and B. Any doubts here? W by 32. So if you go back to our earlier questions, right, very first questions, where we spoke about this. Now let's take the one without any offset, right? Here you are accessing A of TID, and you have your warp size is 16. So you are accessing 16 elements, but the number of memory accesses it takes is actually 1. So it's divided by 16, right? So you have 16 elements per warp here, but you're dividing that by 16 because your memory accesses are coalesced. You're basically doing one access per warp. Similarly here, you're going to be doing one access for all 32 elements. Your warp size is given as 32, right? And that's why along the row, it becomes W by 32. Okay, if that is clear, let's move to the next question. Consider the following code snippet executing on a GPU architecture. The width of the L1 cache line is 64 bytes. Width of the L2 cache line is 16 bytes. Warp size is 16. As we know, the global memory access width equal to warp size into 4 bytes, which is 64 bytes. Now you have memory access that does this. TID equal to block IDX dot X into block dimension dot X plus thread IDX dot X. Out of TIDX equal to in of TIDX. Assume that the number of threads being launched is 256. Size of both these arrays are 256. What is the total number of L1 writes to L2 cache for the given program during the entire lifetime of the kernel? So remember again that the width of the cache lines are these two, 64 and 16, and your warp size is also 16. Okay. If there are no answers, we can take a look at what's the answer. So the answer is 64. So let's see why that is. So let's again start with how many axes do we have per warp. So per warp, warp size is 16 and it's going to be coalesced because we are doing it this way, right? So you would have one transaction per warp. You have a total of 256 divided by 16 warps. 256 is the number of threads and your warp size is 16. So you have 16 warps. So your total number of memory transactions is going to be 16, right? Now, the tricky part here is the L1 cache line size is 64 bytes, but the L2 cache line size is 16 bytes. Now you're asked about the number of writes from L1 to L2, right? During the lifetime of this kernel. So you know that there are 16 memory transactions here, and but the problem is for each of those 16 you have to actually there is this factor of 4 that comes in, right? Because your L1 cache line size is 64 bytes, but your L2 cache line size is 16 bytes. So you need to do a total of 4 writes for each memory transaction of 64 bytes when you write from L1 to L2. So the total number of writes would be 16. The 16 comes from here, and then you multiply it by that factor of 4. So therefore you get 64 writes from L1 cache to L2 cache. This factor of 4 comes in because of the cache line size difference. This 16 comes from how many accesses you have across all warps. Per warp it is 1. You have 16 warps, so you have a total of 16 memory accesses. Any doubts here? Okay, if not, consider the following. Okay, I think this is one of those last week's questions, right? On divergence. I think we had a couple of questions we could not finish. So let's look at this. Consider the following kernel snippet. Kernel 1, so TID is threadidx.x. Mod 2, if TID mod 2 not equal to 0, you come here and you check if TID mod 3 equal to 0, then you do an increment. If not, you do a decrement, and the outermost else you again do a decrement. Now the question is, the increment and decrement operations take 2 cycles each to execute. Assume that all other operations, assignment, conditional statement evaluation, memory access, take no time to execute. This is an assumption. And given this, what is the total execution time for a thread block in cycles where the warp size is 16? So to summarize this question, this kernel, the increment and decrement operations each take 2 cycles. Everything else you assume takes 0 cycles. Warp size is 16. What is the total execution time in terms of cycles for a thread block? Options are 2, 6, 9 and 4. Think about it. I'll scroll back here so that you can look at the details. Six, yes, that's correct. So all you need to remember is that the execution is kind of serialized whenever there are these branches or this divergence, right? So all the threads that kind of satisfy this will first execute and take 2 cycles, then this part and then this part. So it's essentially like serializing it. So it's 2 plus 2 plus 2, which is 6. Okay. Assuming there are no doubts in that, let's move to the next question. This is also, I think, on divergence. So again, you have a kernel and your TID and GID are defined like this. and you have a loop bound defined as thread id x dot x divided by warp size if tid divided by warp size for I 0 till loop bound I plus plus a of gid plus plus. Now there are three different GPU architectures, one where warp size is 8, one where warp size is 16, one where warp size is 32. Now you need to match these three statements to A1, A2, A3. Do they exhibit divergent behavior or not exhibit divergent behavior? So I will leave this for another 10-20 seconds and then move back to the so if you find the options too difficult to kind of get to, you can even say one maps to A or B, two maps to A or B, three maps to A or B, and from there we can figure out which is the right option. So I'll scroll back to the previous screen. So A is divergent, B is not divergent. That's all you need to remember. Now this is your kernel. Take a couple of minutes to solve this. Okay, let's take a look at the answer. So the answer is C, but let's come to that. So the range of values for TID is 0 to 31. Okay, I think this did not mention the block size, so maybe that should have been part of the question. So, considering that the block size is 32, then your values for TID range from 0 to 31. This does not depend on the warp size of the architecture. Whatever the warp size is, the TID values range from 0 to 31, right? Now, this conditional statement that you see here, TID divided by warp size, that it will see that you basically know that threads in a warp will evaluate that to either a 0 or a non-zero value. So let's take one example, A1. So A1 is your architecture where warp size is 8. So you have 4 warps, right, for this block size of 32. So in the first warp where you have thread IDs from 0 to 7, they will evaluate the conditional statement to a 0 value, and the others will evaluate it to a non-zero value. Yeah, basically here your warp size is 8, right? So the first warp, the 0 to 7, will evaluate this as 0, and all the other warps will evaluate it to a non-zero value. So that means that A1 does not exhibit divergent behavior, because your divergence is across warps, where warp 0 goes to one branch of this if, and warp 1, 2 and 3 go to another branch. Similarly, if you change warp size to 16, right, all your now your block size is fixed to 32, so your threads from 0 to 15 will evaluate to one block, and 16 to 31 will evaluate to another branch of this, and similarly for 32, right? So that means that no matter what, the kernel will not exhibit divergent behavior, no matter what the warp size is. So 1, 2 and 3 match with B, and that is your option C. Is this clear? I'll pause here for a few seconds and then we can move on. Okay, divergent behavior basically means if I have a branch, right? So this is my branch condition. Now, if I have some threads in a warp taking one part of that. So for instance, if I have here my if condition is if TID divided by warp size, right? So you have two segments in that branch, true or false, right? And if you have some threads in a warp taking the true fork and some threads taking the false fork, then that is said to be divergent. If all the threads take any given fork of the branch, here for instance we saw that in the A case where warp size is 8, all threads in warp 0 take the same side of the branch, the true case, right? So there is no divergence. Whereas if some threads, like let's say T0, T1, T2 took this branch, and 3, 4, 5, 6, 7 took the false side, then it is said to be divergent, like we saw in the previous example, right? So here for instance, we say that it is divergent because some threads whose thread mod 3 equal to 0 will take this part, and the other threads will take this part, right? So that is said to be divergent. Is that clear? Okay, so I think with this we come to an end of the question. So we have around 20 minutes left. So I'll quickly cover some of the doubts that were asked in the previous two live sessions. So one question was, what is latency tolerance? So it's very simple, right? When threads in one warp execute a long latency operation, for instance, they try to read from global memory, what the warp scheduler does is it will dispatch some other warp, till this operation is finished. Why does it do this? Because of performance reasons. So for instance, in your OS course you might have studied something like, while a process is trying to do some IO, that, or it's waiting for something, it is put to sleep and some other process is executed. Why does it do this? Because this is going to be a long wait, right? It takes a long time to do this. So in during that time, this warp is just going to be idle. So instead, what the scheduler can do is it can make some other warp run. So that way those warps will make some progress during this long latency operation. And there are other long latency operations as well, some branch instructions, some floating point instructions, and all of that. So that's basically your latency tolerance. It's a very simple concept. Okay, the other question I got was to explain this thread number calculation in 3D and 2D with a figure. Okay, so one disclaimer here, this is taken from a blog article. So some of the notation that you will see used in these two formulae might be slightly different, but this is basically so that you understand how to calculate these. So it doesn't matter if the notation is different, right? So here we are calculating the block number and the thread ID in the 2D case, right? So let's take an example. So let's say we are calculating the block ID of this block where both coordinates, the x and y, are 1 and 1. And your grid dimension dot x is 2 here, and your block ID x dot y is 1, and your block ID x dot x is also 1. So this evaluates to 3. And if we actually number the blocks, we also see that block 0, block 1, block 2, block 3. So what is the intuition in calculating in this formula, right? If you had to derive this on your own, how would you do that? So first, what we are trying to do is we are trying to account for the blocks for along a particular dimension. So how do we get that? We get that by multiplying the grid dimension dot x into the block ID dot y. So the y value is 1 here. If the y value was 2, it means that you're accounting for all the blocks in the previous 2 rows, right? So that's why we do this grid dimension dot x into block ID x dot y. So now your kind of, these two blocks are counted, right? But you also need to account for this one block before you can get the ID of this. How do you do that? You take the block ID x dot x. So this is the offset, right? This is the offset of this block. So if I had maybe something like this, right? Let's consider something like this, where I'm talking about a block in the third row. So I have to account for the blocks in the first 2 rows, which I will get by doing grid dimension dot x, which is this dimension, into block ID x dot y. So this much is taken care of. Then for the remaining, for this offset, I take the block ID x dot x. That would account for these two. And you would get the block ID or the block number of this particular block that we are trying to find out. Now similarly, coming to the thread ID. So you're trying to find the thread ID, let's say, again, let's pick something from here. Let's pick this one, 1 comma 1, right? So how do you justify this expression, or how would you derive this expression if you were writing it out? So first, similarly, we need to account for the threads in all the rows that come before this, right? So what you would do for that is block ID. So you know that this block ID is 3. So you know that there are 3 blocks that are kind of already there before you can get to this block, and you want to account for the threads in those. So how do you get the number of threads in each of those blocks? It is block dimension dot x into block dimension of y. That is basically here 3 into 2, 6, right? So you have 6 threads per block. So this part of the expression takes care of the blocks that come before this particular block. These 3 blocks, so 6, 6 and 6, right? 18. So 3 into 2 into 3. So that comes out to be 18. Then what you need to do is account for all the threads in the rows before this thread, right? So just like we did here, grid dimension dot x into block id of y. Now you will have thread dot y into block dot x, right? It's just skipping dimensions if you think about it that way. So that would take care of these three threads. So the thread idx dot y here is 2, and the block dimension dot x is what, 3. Block dimension dot x is 2 into block dimension dot, okay, block dimension dot x. So this comes out to be 2, right? And then finally the thread idx dot x is this right, or did I make a mistake somewhere? Okay, let's go through this again. Block id is 3 and block dimension dot x into block dimension dot y is 6. 6 into 3, 18. Thread idx dot x is 2. Okay, thread idx dot x is 1 here. Okay, I looked at the wrong number. So this is 1. And thread idx dot y into block dimension of x is, sorry, this is 3, right? So 18 plus 3 is 21 plus 1, 22. And if you number these the way it's done in red here, you will see that it's 22. So the intuition is to get this thread ID number by accounting for all the threads that come before it, right? And that's how you can kind of reason out this formula or even derive it if it makes it very hard for you to remember it. And I have linked to the article from where I've taken this figure and explanation. So if you still find it difficult, you can go look at that as well offline. And let's also look through the 3D one, right? So the 3D one, again, I won't spend too much time because it's very similar to this. Again, if you do the block number, thread number and the global thread ID, what you're trying to do is to account for different blocks in different dimensions. So if I'm taking a block, let's say something like this, right? Now I have to account for kind of these two plates that are there before this, right? So that will be the first part of my formula. And then I would have to account for the two things that are below this, depending on how you look through the dimensions, right? That would be my second part of the formula. And then finally the offset from the third axis. That would be the third part of my formula. And working it out like this, like take an example just the way we did in the 2D case and work out the block number, like number it manually, and then also work it out using these formulae, the block number, the thread number and the global thread ID, and that will give you a very clear understanding on how you get these formulae. So I won't spend too much time on this. I think this should make it clear. And then the last question I got was, how do you fix launch parameters given a particular problem statement? So first of all, there is no hard and fast rule on how to do this, right? Your block size and your grid size. So, and another point to remember is it is hardware dependent and it might take some trial and error. So a few things to keep in mind is this dimension can be decided based on the problem data dimension. As we looked at some of the examples in class, if your problem is in a 2D kind of manner, then you would also want to have the grid and blocks be 2D. And secondly, you can get the maximum number of threads and blocks per SM for your GPU. And the other thing that's also suggested is keep the number of threads as a multiple of warp size. And the intuition behind this whole launch parameters is you want to have as many threads as possible so that your SM is fully utilized, right? And you also want to have as many blocks as possible so that utilization across SMs is also good. So these are the major things to keep in mind. And I think we looked at this example in class. So we had something like 16 blocks per SM and 2048 threads. And if we have 128 threads per block, you would have 16 blocks and that would fit into an SM. But if you had 256 threads per block, then 8 blocks can fit into an SM because you hit this thread limit, right? And if you had something like 64 threads per block, 16 blocks can fit because it hits this block limit, although the thread limit is still there. But at this point, only 1024 threads are being used, 64 into 16, which is 50% of your maximum capacity. So this is not very ideal. So these are a few examples to show you those trade-offs. But again, remember that all of these also depend on your register and shared memory usage. So you might launch a certain number of threads and blocks hoping that they would run perfectly parallelly. But because of the memory used, it might not actually fit into an SM. So again, it would involve some trial and error to optimize these things. So I've also linked to a couple of tools that if you want to try out, you can. So one is Nsight Systems. So in class we discussed NVProf. The current day equivalent of that is Nsight Systems. So you can actually run a kernel with Nsight Systems and you will get something similar to the screenshot that I have attached, where you can actually go see some of these parameters and how your kernel is actually running, right? And similarly, the Nsight Compute Toolkit gives you something called an occupancy calculator, which you can use to check how well your kernel launch parameters are suited for that particular GPU. So yeah, these are, I think, the only questions I had gotten in the last couple of weeks. Any other doubts from this week? Okay, assignment 6, questions 2 and 3. Let me take a quick look at them. Sure, I will do this in the next class. I think the solutions are already out, but yeah, I can do this in the next class. I think we have not covered any questions that are similar to this, right? It's asked about memory bus utilization. So yeah, we can look at these two questions in the next class. Anything else that you don't understand or that you would like me to explain? Okay, if not, I think we have around 9 minutes left, but I think this is all I had for this session. So thank you so much for attending. I'll be on the call for another couple of minutes. So if there are any questions or any doubts, you can post on chat and then I'll take it up in the next class. If not, thank you for attending and see you next week.